Alright, welcome back. The next problem will be P1679. It's a fluid dynamics problem, and it's a leak rate problem. So we'll go over it, right? So let's get started. What's the first thing we do when we come upon a problem? Besides change your ink to blue. We look at numbers, right? So 100 gallons per minute leak rate. 60 psig. So I'm going to have to look out for that. That could mess me up, right? I want to keep my eye on that, and 20 psig. So that's a good sign that there's two of them. Looks like we're looking for some sort of gallon a minute, some sort of flow. Alright, so now that's the first thing we do when we see a problem. So when you say, I don't know where to start, that's where you start, okay? Now we read the problem, excuse me. A 100 gallon per minute leak rate to atmosphere has developed from cooling water system that's operating at 60 psig. Which one of the following would be the approximate leak rate when system pressure has decreased to 20 psig? Alright, pretty standard problem. So what they're saying is, you have a pipe. In that pipe is a hole. Out of that hole is coming water. 100 gallons per minute. Excuse me. Inside of that pipe is 60 psig. And what they want to know, as soon as that pressure goes down to 20 psig, what is the leak rate? Now we can get that by this right here. Leak rate squared equals, I'm sorry, not equals, that's a very important distinction, is proportional to dP. Or leak rate, since we're looking for leak rate, is going to be proportional to the square root of dP. And that's going to come because of this. Remember the general energy equation? That's off your handout sheet. That's going to be specific volume times P2 minus P1 plus kinetic energy term, which is going to be V2 squared minus V1 squared over 2GC plus Z2 minus Z1 over G sub C. G over G sub C. And that's going to be equal to 0. Since there's no potential energy change, that equation is going to go out. So now we have dP plus kinetic energy change. It's going to be equal to 0. So we can say that they're actually equal, but we have to know the speed of the pump, or speed of the water coming out of the leak to say they're equal. But to say they're proportional, all we have to know is mass flow rate out of the leak is equal to density of the hole, or density of the fluid, area of the little hole, and speed coming out. So speed is going to be proportional to leak rate, and dP is also going to be proportional to the leak rate. Except it's going to be the leak rate squared because speed squared up here. Okay? And then we can rewrite that to say the square root of dP is going to be proportional to leak rate. Now when we see that proportional sign, that means this. The square root of dP1 divided by the square root of dP2 equals leak rate 1 divided by leak rate 2. Now, we have leak rate 1. It's going to be 100 gallons a minute. We do not have leak rate 2. And we have a dP of 1, which is going to be 60 psig. That's why I said it was an atmospheric leak. The dP is actually going to be 60 psia, or 75 psia, minus 15 psia in the atmosphere. All right, that's one of the advantages of using pounds gauge. So these aren't pressures as much as they are DPs in this case. All right. So the leak rate, the second leak rate is going to be equal to the first leak rate. And then that's going to be divided by dP1, the square root, divided by square root of dP2. Now that is going to equal 100 gallons per minute divided by square root of 60 psig divided by the square root of 20 psig. Now there's other little ways to do that, but this will work. Just plug it into the calculator now. And that's going to be 100. Turn it on first. Clear. 100 divided by let's see, square root of 60 divided by 100 divided by the square root of 60 divided by the square root of 20, and now that is going to equal 57.74. And that, of course, these are going to cancel out. That's going to be gallons per minute. So the second leak rate, 57.74 gallons per minute. Now I look up here at our answers. Is it 33? Is it 53? No, it's 58. Well, no, it's not 58. The NRC man was way off, but we'll spot him 0.26 pounds, or gallons a minute, and say that Charlie is the correct answer at 58 gallons per minute. Then we'll move on, excuse me. So, thank you for watching. That's all I have to say to you people.